My wife loves time travel movies, and one of the advantages, and I'd love to go forward 10 years to see what's going to happen. But one of the things you can do if you're old, you can go backwards really well. And so Berkeley was trying to, kind of publicize its contributions to research, to defend research. And so they interviewed me. And as part of that, I went through my files, and I found a bunch of old transparencies from 1981. So how many of you, there's probably half of you don't even know what a transparency is. But this is a transparency. It's see-through plastic. You can either write on it, or you could actually, if you printed paper, you could transfer it. And this is a little frame to hold them. So how many of you have given a transparency talk? All right, so you can talk to them. Unfortunately, I was hoping we could do transparencies, but I can't do that, so I had to scan them today. But we're going to go back to, okay, whoops, I'm going the wrong direction. Okay, we're going to go back to 1981. You can see at the bottom of the slide, February 17th, 1981. So what was the computer world like then? Mainframes and mini-computers dominated computing. Those were the serious computers. And IBM dominated the whole computer industry. Probably the leading mini-computer, which was like refrigerator size, 2 refrigerator-sized things, was Digital Equipment Corporation. In just a couple of years before they had announced the VAX computer, the first 32-bit address space mini-computer. Intel, the following year, in 1978, announced the first 16-bit microprocessor, the 8086. The IBM PC had not yet been announced in February 1981. It was going to be announced about 6 months later. It would come out with the 8-bit version of the 8086, the 88, and it had 16K bytes of memory in the first personal computer. So that's kind of setting it. The VAX itself ran at 5 megahertz. It had a whole 2 kilobyte cache in the VAX of that time. So set the expectations. The president was Ronald Reagan. Music was disco. Raiders of the Lost Ark came out that time. Okay, so that's where we are. And so this is a talk that I would give. I'll kind of give you the history of Berkeley's involvement in RISC in the talks that I was going around and giving at the time, the slides here. So why were there what we call complex instruction set computers? Fundamentally, the logic was a lot faster than the memory. So in the 1970s, there were still core memory computers. Magnetic core was the core. Towards the end of the 70s, it switched to semiconductor. And then kind of the marketing was, the more complicated it was, the better it was. And then this idea that it would support kind of what was called closing the semantic gap. If you made the instructions richer, that was supposed to be a smaller gap between high-level languages. And so the principles were, and then in the mid-60s, IBM announced the mainframe, announced their family of computers, and they were all compatible, and they used microprogramming to make that work. So with semiconductor memories in Moore's law, the memories got bigger, and since you were doing the control and microprogramming, it didn't cost much to make a much richer instruction set. And then there became the ideas of moving software into firmware, putting in the microcode to make it go faster, and it was supposed to make it more reliable. And then the prevailing wisdom, kind of the sophistication of the architecture, is it looked like the smaller the program, the better it was, so that was the emphasis. And then there's this idea of that we should be raising the semantic gap and and it was called high-level language computer architecture. And registers were this old-fashioned idea. They were hard compilers to use. And so you should do memory-to-memory operations or stack architectures. And this book by Glenford Myers captured it. One's eyebrows should rise when a future architecture is developed with a register and an instruction set, this old-fashioned idea. Okay. What happened? Well, it turned out, as we went from assembly language programming to high-level language programming, we didn't use that many of the instructions. A small subset got used in lots of different architectures. There was what I called irrational implementations. So the IBM 370 had a move multiple register instructions, but it was faster to use simple instructions than the more powerful instructions. Similarly, the VAX had an index instruction, index into array that would check bounds. That was slower than using simple instructions. So were these good ideas? It made things take longer to design. The PDP-1 was 6 months, the VAX was 3 years, and we're in Moore's Law, so technology changes fast. And then there were design years. I just joined Berkeley in 1976, 77, and I did a sabbatical at DEC in Massachusetts because they were having lots of bugs in their microcode. In fact, the VAX 117080 had 4K of PROM, but it had 1K of RAM there as well. There was probably more RAM in the microcode than there was in the caches. And there were bugs all the time they had to fix. Okay, so this kind of, I came back from sabbatical in 1980 and kind of reflecting on the difficulties and the use of the complex instruction sets. These were the principles that guide us. So keep things simple unless you have this very good reason not to. You might execute fewer instructions or fewer cycles with a complex instruction set, but you might increase the clock cycle time that offset that. Micro-instructions, if you keep the instructions simple, the micro-instructions aren't faster than that. And there's no magic. Just because you call it microcode, it doesn't magic. It's just another instruction set. And rather than program size being the most important, it was keeping the instructions easy to decode, and pipeline execution was much more important for performance. And we ought to use compiler technology to simplify the instructions. And so to kind of make fun of the complex instruction sets, I'm a car guy, so I used the old 1950s Cadillac as a fair and accurate representation of complex instruction sets. And we had this cool sports car for RISC. But then the questions was, all those questions on the slide, performance, design time, and so on. So kind of in the middle of this effort in the summer of 1980, it looked like these ideas were going to work. I thought the ideas would work. So I thought it'd be but we weren't sure they were going to work, but I thought they might. And so I wrote this paper during the summer on the case for the reduced instruction set computer with my student, David Ditzel. And we submitted it to the magazine at the time. It was Computer Architecture News that virtually every computer architect got. And it showed up in September. So as is my nature, when I wrote it, I had just been on sabbatical at DEC, and I was talking about the VAX quite a bit. So I sent it to my friends there, Douglas Clark and Bill Strecker, the architects of the VAX, to get their feedback. I thought they'd write comments. Instead, what they did is they wrote a rebuttal. And so in the September issue of Computer Architecture News, there was the case for RISC and the case against RISC right side by side, and people read that. So that led immediately to controversy, and everybody likes controversy. At the first ASPLOS conference here in Palo Alto in 1982, we had a debate of RISC versus CISC, and that was such a popular. We did it 3 times in the next year of the RISC versus CISC debate going forward. Okay, so we had these ideas on paper, but we had to build it to show that it would work. And so, using these frames, we had what you'd call animation today, which was we just have little pieces of plastic attached to the frame, and we'd animate it by turning it over. So I will show you the animation there. So how could Berkeley compete with industry? It took them 4 to 7 years to do one of these processors. What did Berkeley have going for it? Well, we had Berkeley computer-aided design. We had released, we thought, very good CAD software. It took $30 million back in 1980 to do it. We had the reduced instruction set. That should be a lot easier to do. It took them 100 man years. We had 2 Berkeley student years working on it. And they had experience, but we had beginner's luck. All right. Now, how we actually did it is we did it as a series of classes. Back in 1980, Berkeley was on the quarter system. It's on the semester system now. So I just came back from sabbatical, talked about my experience with my colleague, Carlos Acan, and kind of like, is keeping things complicated the right things to do for microprocessors? Now, there was this, the real industry was the mini computers and mainframes, but we believed in Moore's Law, and we ultimately, the microprocessor was going to be where the action was. And so we then in a graduate class at Berkeley, we explored the ideas of this high-level language computer architecture, CISC, and well, what we then called CISC, but the RISC ideas really. That summer, we came up with the design of the draft of the RISC-1 instruction set. And it's amazing, the RISC-V core instruction set and the RISC-I instructions are very, very similar instruction sets, surprisingly similar. The RISC-V core is a little bit more elegant than the one, but they were surprisingly close. That fall, the students learned how to design chips, the so-called Meade-Conway course, and then there were 2 more specialty courses where they actually did the layout of the design and sent it out and brought it back for testing. And the arrow means that's where the slide was. So this was February of 1981. Okay. Basically, largely software people, computer science people were trying to design chips. How do we, and it was, a dozen people working on this. How do we coordinate? Well, we used some software techniques from the Unix systems that were there, source code control systems, mail and messages to communicate, and then a series of tools, some of which were invented in the classes. So Dan Fitzpatrick and Bob Smelik were students in the class, and we needed things to make it work, and so they invented stuff to do it, and then we shipped it out over the ARPANET, and DARPA fabbed it came back. Back then, if you did a new architecture, you needed a new operating system. So the VAX architecture had the VMS operating system. Well, at Berkeley, they were working on Berkeley Unix. And it was this new idea of a portable operating system. There wasn't written assembly language. So my favorite operating system moved, so we didn't see there was going to be any problem there. It ran on 68,000s. We thought we had everything to 68,000, so we didn't see that being a serious objection. So then, it all comes down to performance. So running, a preliminary set of benchmarks, we have the VAX mini computer, which was kind of the standard everybody compared it to. This, it was 30 professionals by 3 years. It was in 1978 bipolar technology. The next ones are all microprocessors in, 78 to 79, NMOS technology. Again, professional programmers with, tens of them for a couple of years. So we were going to do it at Berkeley with, kind of 10 people times 1 year with a bunch of amateurs in an older technology. So I wrote on the slide, if in March of 1980, right when we started the process, if you were going to bet one month of salary, what fraction of a VAX would be the goal? So to poke fun at my friends in industry, that we put the mini computers in part. This was the average of 11 C programs. With the VAX with the big Cadillac, and then there's an Edsel, a famously failed car from BB&N, and then some microprocessors there. So it turned out that the RISC-V, RISC-I was about twice as fast as VAX, so a big success. There was no spec benchmarks then. We just ran a bunch of small programs. Spec wasn't invented until 1989 or so. So we had to do it with a lot of small programs to be able to drive it. But yeah, that's kind of how we got our numbers. So fast forwarding, or if I look back in 1981, our time travel 45 years ago, those were the people who did RISC. There's Carlos Sacan and I as the faculty, along with John Osterhout, who led the CAD efforts, and then a lot of graduate students who worked on the RISC project. 10 years ago, IEEE put a plaque at Berkeley to recognize the first RISC microprocessor. And as part of that ceremony, we brought people back, and you can, the older people in the back that's what happens in 35 years. If you look, I'd say there was a lot more hair back in 1981. And the people in the lower right on that slide are RISC-V. So we had the RISC-I people come back and meet the RISC-V people in 2015. And that's Yunsip Lee, Chris Celio, and Scott Baden, all who played this important role. So it was a fun kind of cross-generational interaction about RISC architectures now and then. All right, with that, I'm all done. Thank you.